Welcome to JupyterCon2020. I'm your host, Joe Spisak. I'm the PyTorch Product Lead at Facebook. Today I'm going to be talking about deep learning development with PyTorch and Jupyter. A little bit of background on me. As I mentioned, I work in PyTorch here at Facebook. I've been with Facebook just under 3 years. Previously, I was at Amazon working on product and partnerships and AI. And then prior to that, I was with Intel leading ML strategy for mainly the cloud group. I'm extremely passionate about the intersection of open source, AI, and community building, and that's one of the reasons I really, really love Jupyter. And it's this project that brings people together, allows them to collaborate and execute code quickly and experiment. It's a match made in heaven for machine learning. So I'm here to talk about PyTorch. So PyTorch is an open source project. It has an incredible following of developers and contributors and community members globally. You can see here is the GitHub site. It's github.com/PyTorch/PyTorch and the PyTorch org. When we think about the project itself, we think about a number of kind of key tenets. One that we need to be able to ship and scale. So we need to be able to support this Pythonic eager mode, where it feels like you're writing Python and defined by run type of paradigm, but also that at some point you need to get to a graph where you can actually execute that efficiently, billions or even trillions of times. Secondly, it's dynamic. So things like variable data lengths or control flow should be allowed. Distributed training support for these leading edge architectures like say GPT-3 or even these larger models that are coming out where they just can't reside on a single compute device or even a single server. Speaking of hardware acceleration, things like Cloud TPUs are really changing the way researchers are able to operate in this, being able to train a number of different models in parallel or even at larger scale. And then lastly, this simplicity over complexity. When we start a new feature on PyTorch, we think about what is an elegant API that's really going to make researchers and users productive. And if we had to boil down kind of the fundamental essence of what PyTorch is trying to do, it's really this research to production paradigm. How do I take this any idea that you can express as a researcher, as a user, and take it into some type of product deployment or production deployment and really create that flywheel in between. We see so much value being created by the research community, whether it's in academia, whether it's in industry labs, and there's product value, there's actual value in better translations, in better natural language processing, better computer vision for a number of different applications. So when we think about PyTorch itself, it's this kind of monolithic library, but no, it's actually a subset of methods and libraries and APIs and tools that you can use to, in the end, build amazing neural networks at scale. And so we have a number of APIs like TorchNN, which really is how you define a layer of a neural network. Things like torch.data, which allows you to say load a data set, batch up data and load it as you're training, or even libraries like Torch Vision, which provide models and data that are easily accessible for kind of cutting edge or state of the art computer vision. So let's talk about the community for a brief bit here. So when we think about the community, it's academia, it is industry, and you can see some of the different players, whether it's Alfredo Canziani over at NYU, Jeremy Howard, who literally has tens of thousands, if not hundreds of thousands of developers on Fast.ai. Absolutely globally, he teaches them for free in his MOOCs, whether it's industry labs like Tesla and Dolby, or even like the partnership we had, for example, with Google and Salesforce to bring Cloud TPUs to developers. We've also seen a number of companies like, for example, O'Reilly talking about how researchers use PyTorch and how much they love it, and Preferred Networks, which is a Japanese company. There's a strong partner and strong community member. They were the originators of Chainer, which is another framework, and had since gone all in on PyTorch. And then, of course, OpenAI, a thought leader in the space, went all in on PyTorch earlier this year, which was super exciting. So let's get into the numbers. So when you look at the project itself, we're roughly at 1,600 contributors, and that is a growth year over year of over 50%. And if you look at the PyTorch forum, where most of our issues and discussions happen, kind of like the Stack Overflow of PyTorch, we have over 34,000 active users on the platform discussing, helping each other out. It's really amazing. And then if anyone hasn't gone to paperswithcode.com, it's a really great site. They have this thing called the Trends. And Trends actually tells you over time some of the really interesting metrics in open source. One of the things that it actually tells you is how many paper implementations, how much code was generated alongside a paper. And you can see here, I've kind of grabbed the snippet and forwarded it out in time to basically the current time here in September. And you can see red there is PyTorch, which we're really proud of. And you can see it's growing quite quickly, kind of vis-a-vis other frameworks, which is really amazing. So I want to briefly talk about PyTorch at Facebook. So when you think about the products that we use or that we leverage AI in, you can see here's your canonical Facebook Blue app, where we're doing things like search and tagging faces, and we have newsfeed for recommendations, or serving ads, or doing translation in real time. And of course, that can be something in Messenger and some of the other products and services we have. Also in things like on-device. So this is a portal. If anybody hasn't seen a portal, with, of course, COVID, I use a portal almost every day with meetings and such. And this is all running on-device. So the neural network is running resident on the portal device itself. It's using Mascar CNN, which is a computer vision architecture for detecting, say, key points, or segmenting and detecting objects within images, and actually using that as a guide to guide the camera. So switching gears over here to Jupyter, because we're here to talk about Jupyter. And Jupyter plus PyTorch, in our mind, is definitely equal to love. We absolutely love Jupyter. We love notebooks. It's by far the easiest way to get started and interact with deep learning and machine learning. So when we started building our site for PyTorch.org, one of the things we thought of is, we wanted to work with some way to get developers and kind of an easy on-ramp to just playing with PyTorch. And so we partnered with Google, and Google has a really great project called Collaboratory, canonically or colloquially called Colab. And so Colab is kind of this place where everyone goes that can run notebooks. There's free GPUs, CPUs, TPUs, the tensor processing units, and it's just this great interactive thing that you can run for 12 hours without any kind of credit card. And so, after working with them to get native support for PyTorch some time ago, we now have it, and we've even gone further and we're able to add it into other places where people can use it. But there's really two options to using PyTorch in Colab. One is just putting the GitHub link into Colab itself. So if you go to colab.research.google.com, it will ask you to load a notebook in some way. You can click GitHub and then put in the link. This one way. The easier way is option two. And if you go to pytorch.org, and I'll show you a little more later on, you can actually go to our tutorials themselves and either download the notebook itself, which gives you kind of the IPyNB formatted file, which can be loaded either via Colab or through kind of standard Jupyter, or you can click on this nice handy run in Colab button, and you're kind of off to the races. So here, this is what would happen if you click on it. You would end up in this nice IPyNB formatted file within Colab that is connected all freely to GCP, to Google Cloud, with a CPU. And then what I can do is I can then change that runtime. If I go into the notebook settings and change my runtime to either support GPU or TPU. So it's really, really handy. Really easy to use, and you can immediately just start interacting with your notebook without setting up an SSH tunnel or having to spin up any kind of separate Jupyter instance. And if you want to try this out, a great way to do it is to go to pytorch.org. You can click on the tutorials. Also, we have shorter form recipes that also have Colab integration. And you can also, of course, download the Jupyter notebooks themselves. And then just a shameless plug for all the channels where you can learn more. We have, of course, our canonical site, which is pytorch.org. We have a Twitter channel, YouTube, Facebook, and Medium, where we post dozens of blog posts with the community. And almost every day we post something new. But of course, we're here to talk about Jupyter. So shall we look at some code in a Jupyter notebook, of course? Okay, we are back to deep learning development with PyTorch. This is Joe Spisak again. This is the practical side of the talk around PyTorch and Jupyter. So a brief agenda here that we're going to walk through is just an intro to PyTorch, very brief, just to give everyone a bit of a flavor of it. We will develop a fairly simple model, mainly because it takes only a few minutes to train on only a few epochs. So it won't take very long. And we'll, of course, do that in this handy Jupyter notebook, which I will be sharing with everyone in Colab. It'll show us how we handle our data, how we do our model development, how do we train it. And then we'll finish up with visualizing loss curves, and we can actually visualize the data itself and actually look at the graph itself within TensorBoard. And then we'll finish by actually evaluating the model and showing how it does on predicting on new data. So first off, we're going to go into our runtime real quick and just make sure our runtime is set to GPU. You can see it is. We're in a Conda environment, Python 3. We'll save that. And then from here, we can actually start to execute some code. So you can see we have all of our import statements, starting with like matplotlib, numpy. I've added some nice code comments here that kind of give everyone a little bit of a flavor for why we're importing these things. We have our standard PyTorch imports like Torch Vision for computer vision, PyTorch itself, the transforms we use for manipulating data, and then a number of handy modules like Torch NN, the functional API, as well as Torch Optum. This is what we're going to be using to build our network. So let's shift enter on that. And that executes. Now we can check and see what GPU we have. So if those of you aren't familiar with Nvidia Smi, this is a command that basically gives you information about the GPU that is resident on your machine. So I can hit bang Nvidia Smi. This gives me the readout. I have a Tesla T4, so a fairly newer generation GPU. Again, in Colab, it's free. And it's a bit of a luck of the draw with Colab. So you never know what you're going to get. Could be a P100. Could be a K80. That's kind of the fun of Colab. And now we can actually get into code. So everything's imported. We have PyTorch available. We have a GPU. And now we can start doing basic things. Like I've just created a 5x3 matrix of random numbers, which I can then print. And I can just keep printing that and generate random numbers, similar to, of course, like something like Numpy. I can also define a data type. In this case, these are long tensors. So these are like 64-bit. And this is another 5x3, 5x3 matrix of ones, actually, but I'm printing X here. It looks like I have a bug in my code. How fun. In this case, so there you go. So I was actually trying to print X, which is what I defined in the previous one. In this case, so I'm printing Y, which is just a factory function for how you define a matrix of ones. And if I want to add these up, I can add X and Y, and you can see the two add up to the matrix we get here. I can also do like all kinds of NumPy style indexing. So in this case, if I shift enter on this guy here, you can see my matrix up above. I have X, so I'm grabbing, what is this, 0.34 down to 0.50. So this is the first, so 0 indexed, the first column of this matrix. And of course, I can play with this, and I can get the third one, again, 0 indexed, and so on, or change it to the row, or index to an exact entry, exactly how I want to. We can also do things like convert torch tensors into NumPy arrays. So in this case, I'm doing, again, a factory function of torch ones. In the case of, I'm going to give a 5 entries in the tensor. And then I want to be able to cast that into NumPy to give myself an array. So I can just do this b equals a dot NumPy, which gives me, and I print b, which gives me an index, an array instead of a tensor. What's nice is I can also just also force computations onto GPU devices. And what I've done is a quick if statement, just to protect myself if I maybe don't have a GPU on my machine. Maybe I don't know, but I have this handy if statement. So I just do a handy, if torch.CUDA is available, and then set a device as CUDA GPU. I can then run this and use this argument within the command here to set device equals device, and then which is in this case CUDA device, and I'm creating a couple of different variables here, adding them together and then printing, and then I can just go ahead and execute this, and this will actually run on the GPU. And again, if it's going to be not available, if there's no GPU on our machine, then it will default to the CPU. In this case, running on double precision. So super handy. Okay, that was pretty basic stuff. Now we can actually move on to something that's really interesting, and that is, how to actually train a network. So I thought about doing the basic MNIST, which is pretty boring these days. I think everyone is kind of seeing how you can classify numbers. So I figured I would grab at least the Fashion MNIST dataset, which is the same exact 28 by 28 grayscale images that Jan LeCun had developed for the original MNIST dataset. But in this case, it's articles of clothing. So it could be boots or trousers or handbags or what have you. So you can see this is actually a printout of all of the images in the dataset. And so first thing we need to do is actually load our data set. So the nice thing is we have some really nice utilities in Torch Vision that allow us to kind of take these different transforms and compose them. So in this case, we're just doing some basic normalization to actually normalize the images. We're going to load the data set itself, but we're going to split it into the test as well as the train set. So you want to always train on a portion of your data, and then you want to be able to hold out a portion of your data set when you want to actually test it. And this allows you to understand how your network's actually generalizing to new data. I then set up a train loader, and this allows me to batch the data when I want to train, as well as a test loader. And batching will make things go faster, and I can set the number of workers and so on. I'm also setting a number of classes. So again, here's my labels, t-shirts, trousers, pullovers, and so on. And I've done a quick function here in matplotlib in order to actually visualize a few of these images. So I'm going to shift enter on that. And that should give me all of my data sets loaded up. And now what we can do is actually visualize a few of them. So I'll shift enter in here, and I kind of ruined the surprise there by previously executing it. But you can see some of the images here. These look like some kind of shoes, I guess, ankle boots, and so on. Okay, so we kind of know what our data looks like. We have it loaded up. We can now define our network architecture. And again, in this case, we are training on a fairly basic network. I lied, it's actually not a CNN. I just grabbed an MLP, which is a multi-layer perceptron with a number of fully connected layers, basically. So in this case, we're using the NN module. So we're calling this a class classifier. So define this class that's called a classifier, and we're subclassing it on the NN module portion of PyTorch. And what that does is actually allows us to pull layers and define these layers. In this case, the nn.layer API. And that gives us a nice linear layer, and then we can basically define the size of those layers, basically the number of inputs and outputs, and how they kind of map down into their output, which eventually leads to something that's 10, which is the number of classes that we're actually going to be predicting. We then define a forward method, and what this does is, well, first of all, you flatten your input tensor. That's and use the dot shape and the view API to be able to flatten that so that it gives your network something that it's expecting, the shape that it's expecting. But then you actually define things like your rectified linear unit, which is a nonlinear function that basically takes a linear layer and adds nonlinearity to it over and over again. If you've studied neural networks, you know it's typically a linear, nonlinear, linear, nonlinear, some combination of those that basically brings the power of the prediction. Otherwise, you'd have just one linear function. And then what we're doing is we have a number of these rectified linear units followed by a softmax, which actually will give us a prediction. And so we'll shift enter on this. And this actually has now defined what our neural network is going to look like. And we can visualize this later on in TensorBoard. Before we can do that, before we can actually start training things, we need to do a few other things. So we've imported Torch Optum as Optum. This is an optimizer library. So if you have heard of things like Atom, the Atom optimizer, this actually falls in that library, or terms like stochastic gradient descent that provides us those tools, those as a library. We also need to find basically what our loss function is. In this case, we're using the negative log likelihood loss. And this is kind of how we're judging how good our neural network is doing. And then, of course, our optimizer along with our learning rate. And don't worry too much about the learning rate. You can look it up. But this basically is how far we want our steps to be, like how when we're doing our optimization, do we want a small step, a big step? Too big of a step means you might actually diverge your network. Too small of a step means you actually might never actually converge because it may just take forever to actually train. So we are going to shift enter on that. And then, so basically we have everything set up pretty much for our neural network. Now we want to start setting up TensorBoard. So for those who haven't tried TensorBoard, it's a great library that was developed by Google, and then we partnered closely almost 2 years ago, I guess now, to support PyTorch natively. And so you just have to do a simple from statement. So from torch.utils.tensorboard, import summary writer, and basically you have the full power of TensorBoard. So firstly, I want to default to a logdir, a log directory, where my runs are going to be resident. And you can see here, I'm defining that as run/fashion_mnist experiment 1. I'm going to close my writer. So TensorBoard knows that I've defined this. And then actually I have called this command called load ext TensorBoard. And this is a super handy API that allows you to use TensorBoard within Jupyter. So we are going to run that. That takes a second. We can also use TensorBoard to visualize data. So I have a few extra commands here that allows you to use TensorBoard to visualize. And you can see I'm loading up a few random training images from our train loader that we defined earlier. We're also going to create an image grid. So Torch Vision provides a really handy grid to simply visualize a few images in your training set. And then we actually just want to write to TensorBoard. So we use this command called write.addImage, and then basically feed it, feed it an argument. And if I click on that, I can actually visualize data just purely using Torch Vision. Okay. Next with TensorBoard, I want to actually visualize my graph. So this is the actual graph of the neural network. This is the DAG, the directed acyclic graph. And this is like how you feed data all the way through to an output and how the neurons essentially connect up. And so we just want to define this as this writer.add graph with models and images, and then close that again, just to tell TensorBoard that is done. Now I have my training loop. This might take a few minutes. So while it's training, I will talk through what this training loop is actually doing. So I've set my number of epochs up to 3. So epochs is essentially one iteration over the entire data set. And it's typically how you measure, how many times you're actually going over the data and how many iterations your training loop is actually going to execute. And typically, though, to train a larger neural network, you'd probably train something maybe like on the order of 60 or 100, or even sometimes even more epochs. In this particular training loop, I've actually defined the writer as summary writer. So I want to make sure that when TensorBoard executes later on, that it actually is going to be visualizing every epoch. I set up a quick for loop here where I have my images and my labels. So there's my kind of XY pairs, so to speak. If you're familiar with how supervised learning works, I'll skip to a few of these things. I want to zero out my gradients before I start actually running my network. So we start from a base of everything as 0. We call loss.backwards. So typically with neural networks, you have a forward pass of data through your network. You take a backward pass, and then you take an update, or you do an update step. In this case, that's our third step. We take the step using optimizer.step. Then I calculate my loss, see how I'm doing, and then I will start to print that out. And you can see we're already printing out our training loss, and I'm dividing that by 1,000. So it's just something that is a little more kind of visually understood. And you can see the numbers going down. This is a good sign. We want this loss to be very low because that's actually means the more accurate our model is actually going to be. So this will run one more time, and then we're going to actually execute TensorBoard and get that going. And you can visualize everything in TensorBoard. So if we give that one more second, we'll get down to the TensorBoard piece. There we go. So we have actually run 3 epochs on our network. Again, fully connected multi-layer perceptron, trained on the fashion MNIST data set. So let's execute TensorBoard. So now we're launching TensorBoard. And for those who use TensorBoard, you're going to be pretty familiar with this. And you can see very quickly what is available. So again, I only trained 3 epochs. You can train a lot more. I've trained this 10, 20 epochs, and it gets better and better. And what you'll see is actually it's generated based on all those hooks that we put in our code. It generated 3 things. It generated some scalars. It generated some images, and it generated a graph. And so why don't we go through these one by one. So in the case of the graph, so we actually are showing the actual connections of the graph itself. So here's input where you'd have, say, this like 1 by 28 by 28. So one channel, grayscale, 28 pixel by 28 pixel set of images batched in 4. That is there. That's your kind of X input. And those then propagate through these linear fully connected layers to this output classifier here. So that kind of is a very, very simple graph. It's not that exciting. You can imagine, though, when your networks get really, really huge, this is super handy to be able to show where things are connected and maybe things are broken. You might need to adjust how your network is architected if it's not training, or maybe it's training suboptimally. And then secondly, we logged some images in here, and you can see we're visualizing our data set, or at least a few images from the fashion MNIST experiment 1, if you remember earlier on. And so you can visualize data here. And then our scalars, this is actually our training, the data, actually the epoch, the loss data from every epoch. And you can see, this is really handy. You can see it going down, and that's really handy. So if you look at all of that, we've actually trained a neural network, and now we can actually classify it. So this is actually just a handy function that I created that creates a visualization, and we can actually start to plot some inference results. And so you can see all of our labels here, and we're basically going to be showing our class probability based on the predicted from the network. And so here we go. We've actually just executed this little function. You don't need to know too much about what's going on, but it's a handy one that you can copy and paste if you want. Now we're ready to actually do some predictions. So in this case, we're actually just setting our images and labels to our test loader. So remember, we defined that earlier. We are actually just defining basically our predicted outputs in order to make sure that they look like probabilities, and then actually using our model to do a prediction. And in the case of this, we're actually just defining like the image as the second image in, say, a batch. And I can change this to 1 or 2 or 3 or whatever, and we can do a couple of them. So if I just hit enter on this, you can see I picked the second image in this batch, and it's a pair of trousers, it looks like, and it looks like we have a pretty strong affirmation that that is a pair of trousers. I can change this to, say, the 0th in the batch. And you can see this, I guess, is a boot. Also might think it's a sneaker, could also think it's a sandal. So there's a bit of dissonance here with the model and what it wants to predict that it is. But overall, it thinks it's a boot, it looks like. And we can continue to do this and do other predictions. So I guess that's still a trouser. I think this is, looks like that is a pullover. I'm not sure how they can tell it's a pullover, but it looks like it's the model is very confident that that's a pullover. So that's it. I will share this notebook in GitHub. You can go to pytorch.org. You can play with tutorials, blogs, check out all the educational materials, plus all tutorials have Jupyter notebooks and direct links to Colab. So enjoy. Thank you.